Hey everyone, and welcome. Let's jump right into this explainer and unpack the fascinating journey, the underlying mathematics, and the absolutely profound real-world impact of artificial intelligence. I mean, whether you're trying to navigate some new software at work or just reading the daily headlines about the future of humanity, AI is literally everywhere right now. So today, we're going to break it all down. Our goal is to give you a crystal clear, structured understanding of why we even need this tech, how these systems actually work under the hood, and where they're heading next. Okay, so here's our roadmap for today. We'll start with the quest for intelligence, then cover a brief history of AI, move into the architecture from ML to transformers, look at AI in the real world, discuss why we need rules, and finally look at the future of AGI. Section 1, the quest for intelligence, humanity's search for thinking machines. Let's get right into it. So, can machines actually think? Back in 1950, when computers were literally these massive, room-sized beasts that barely had the processing power of your kitchen fridge, the brilliant British mathematician Alan Turing posed this exact question. Now, computing power was super limited back then, so Turing couldn't exactly build a thinking machine on the spot. But he did propose something called the imitation game. You probably know it today as the famous Turing test. It was designed to see whether a machine could exhibit intelligent behavior that was totally indistinguishable from a human. It basically set the ultimate benchmark for the field, way before the field even existed. Moving on to Section 2, a brief history of AI, from theory to reality. If we look at the historic perspective, AI's timeline is, honestly, a total roller coaster. It officially kicked off in the summer of 1956 at the Dartmouth Conference. That's where John McCarthy actually coined the term artificial intelligence. But progress definitely wasn't a straight line. By the 1970s, after researchers kinda overpromised and underdelivered, the whole field entered these massive funding droughts, which became known as AI winters. Things were pretty quiet until about 2012, when everything dramatically shifted. The deep learning boom took off, completely fueled by insane growth in GPU processing power and massive new datasets. And then, 2017 hit. The introduction of the transformer architecture completely revolutionized the field. It essentially catapulted us into the modern era of generative AI. Section 3, from ML to transformers, the architecture of intelligence. All right, let's delve into the modern structure. Think of AI architecture like a giant set of Matryoshka nesting dolls. At the very outermost layer, the biggest doll, we have artificial intelligence. It's the broad, overarching capability of computational systems to perform tasks we usually associate with human intelligence, things like problem solving and perception. Essentially, it's the umbrella term for the entire pursuit of making machines smart. Now, pop that doll open, and inside we find machine learning, or ML. This was a massive paradigm shift. Instead of a programmer painstakingly writing out explicit step-by-step rules for a computer, machine learning lets the program analyze huge datasets, find the patterns on its own, and automatically improve. You basically just feed it the data and the expected answers, and the machine figures out the relationship between them. A real game changer. Zoom in one more time and boom, we hit deep learning. This is where the absolute magic of the last decade comes from. Deep learning uses these stacked neural networks. They're multiple hidden layers of artificial neurons, loosely inspired by how the biological human brain works. These layers team up to progressively extract more and more complex features from raw data. So if you feed it an image, the first layer might just see basic edges. But as it goes deeper, the next layers start identifying complex shapes, like, say, a human face. Now, you might be wondering, what's actually under the hood of modern large language models? Well, a recent, incredibly rigorous mathematical paper beautifully demystifies the whole transformer architecture. They proved that a transformer isn't just some mysterious black box. It can actually be interpreted as, and bear with me here, a discretization of a continuous integral differential equation. I know, that sounds incredibly dense, but what it essentially means is that the way these models process human language is deeply grounded in continuous mathematics. It directly connects these neural networks to the exact same types of differential equations we've been using in physics and engineering for years. Okay, don't let the math scare you. The main takeaway here is that instead of magic, the architecture relies on very specific, discrete mathematical steps to crunch language and sequence data. The paper points out that self-attention, which is the vital mechanism that helps the AI figure out which words actually matter most in a sentence, emerges naturally as what they call a non-local integral operator. And layer normalization, the thing that keeps the neural network stable, that's mathematically characterized as a projection to a time-dependent constraint. The so what here is that by understanding AI as this dynamic, predictable mathematical system, researchers can build much safer, more robust models. Let's look at Section 4, AI in the Real World, Practical Applications. Let's zoom back out and talk about the real-world significance of all this dense math. How does it translate to the software on your laptop right now? Take the creative industry, for example. The late 2025 release of Adobe Illustrator 2026 directly integrates these advanced models right into the workflow. We're talking Firefly-powered tools where designers can use Place from Adobe Cloud to drop AI-generated art straight into their projects. There's this crazy new beta feature called Turntable that lets you instantly view 2D vectors from 3D-ish angles, plus generative expand for smart resizing. The AI isn't replacing the designer here, it's stepping in as this highly capable sidekick that just instantly handles the tedious stuff. Section 5. Why we need rules. Global regulation. Because these tools are seamlessly entering our lives and getting so incredibly powerful, we desperately need global ground rules. But defining exactly what to regulate, that's the huge hurdle. UNESCO actually notes that because AI evolves so fast, we need a dynamic, really broad definition. If we just create fixed rules based on today's algorithms, our policies are going to be completely outdated by tomorrow morning. We literally have to future-proof the regulations. To tackle this impartially, lawmakers are starting to draw some very strict boundaries. The European Union's AI Act, for example, takes a risk-based approach. They are strictly banning specific practices by labeling them as unacceptable risks to fundamental human rights. This legislation bans things like harmful AI manipulation, government social scoring, using emotion recognition in workplaces or schools, untargeted scraping of the internet for CCTV facial recognition, and biometric categorization. It's all about ensuring that while we let innovation thrive, we absolutely do not compromise fundamental human rights. And finally, Section 6, the future of AGI, blending logic and intuition. So what does the future actually hold as we race toward artificial general intelligence, or AGI? To understand that, we need to look at a massive historic divide in AI research. For decades, the community was totally split. On one side, you had symbolic AI. It was amazing at rigorous, step-by-step logical reasoning, but honestly terrible at handling messy, unpredictable real-world data. On the other side, you have modern neural networks. They are fantastic at intuitive pattern recognition and statistical probability, like sounding exactly like a human when writing text, but they really struggle with strict deterministic reasoning and multi-step math. They can give you an incredibly confident answer that is just completely wrong. So both approaches hit a wall when it came to true generalized intelligence. But the landscape is shifting rapidly. As of April 2026, we're seeing this massive breakthrough with something called neurosymbolic AI. It's a hybrid architecture, and it's exactly what it sounds like. It takes the intuitive, pattern-matching superpower of deep neural networks and smashes it together with the strict, rigorous logic of symbolic reasoning. Researchers are calling this cognitive density. It means the AI doesn't just predict the next word, it can actually verify its own outputs using strict mathematical logic. It's a huge leap forward. And as these models gain this crazy level of cognitive density, keeping them safe and aligned with our values is absolutely crucial. That's where RLHF comes in. Reinforcement learning from human feedback. Basically, it encodes human input directly into the training data. By rewarding the AI for safe, helpful responses and penalizing it for bad ones, developers are making sure these systems closely mimic human preferences and ethical behaviors. It stops the AI from just being a cold, calculating machine and gives it a sense of our values. So as we wrap up this explainer, I want to leave you with a question to really chew on. We're currently mapping out the deep continuous math of neural networks, we're finally bridging the gap between statistical intuition and strict symbolic logic, and we're laying down global laws to protect our rights. As we master these algorithms and firmly set our boundaries, what do you think humanity's ultimate artificial companion will truly look like? Thanks so much for exploring the mechanics and the future of AI with me.